Okay, so we have three types of radiation. Who is the scientist who separated radiation into these three types? Ernest Rutherford. Very good. Ernest Rutherford. Okay, and what three types did he discover for us? Here you have alpha, beta, and gamma radiation. Okay, the three main types that he discovered. Give me something about alpha particles that we talked about. Okay, it's a positive charge. Good. So positive charge particle. Dangerous? Oh, Devin? Okay, so the particle is actually a helium particle, so it looks like this. Okay, so we talked about the symbol, so it's an actually helium particle, but it's a charged one. Not dangerous to us. Right, so a piece of paper can block it, shield you from it. It's not going to hurt us. What else do we know about it? Oh, the symbol. What's the symbol for it? Yeah, it's like a backwards A or a fish or something like that. Okay, you might need to know that for the test. Okay, symbols. Okay, beta radiation. What do you know about beta? Okay, so negatively charged. And what kind of particles are these? Okay, and these are high-speed electrons. Very good. Not that electrons are already going fast, but speed of light. They're high-speed electrons. Okay, so that's kind of what's happening. They're negatively charged, high-speed electrons that are zipping away, okay, bombarding you. These are a little bit more dangerous than alpha particles. What symbol do we have here? I have two symbols. What's that? Yeah, it's like a B with a tail to it, or we can have an E, and then at the top and number bottom, or number. What number goes on top? 0 bottom, -1, and same for this one. So they mean the same thing. Okay, so I'm going to use the E for us, but you might see as a B as well for beta. Okay, know that symbol for the test. Okay, so alpha symbol, beta symbol, and then gamma radiation we didn't talk about. We just said this was high energy, mutate your DNA, very, very, very bad for you. That's not part of our discussion for radiation up here. You might get that a little bit later in geology. Okay, so gamma radiation, very, very bad for you, high energy. It can mutate your DNA, your cells, that sort of thing. Very, very harmful to us, to humans. Okay, then what do we mean by radiation then? What is radiation? What's that? There we go. It's a spontaneous release of energy. So we have substances that in nature are just releasing energy by themselves. Okay, we're not making it do it. We're not using chemical reactions to make the energy release. We're not zapping with electricity. The material itself is just releasing energy by itself. Okay, we want to understand why it does that today with what we call nuclear stability. Okay, so that's our objective. We want to understand why some substances are releasing energy spontaneously. Okay, and the energy is going to be in the form of alpha particles. The energy release could be in the form of beta particles. It could be in gamma too, but we're not going to go there, right? So the energy that's being released is spontaneous, and the energy is either alpha or beta radiation. Okay? Sorry, so that's our goal. Got it? This is the essay for the test. The essay for the test is to explain nuclear stability. Okay, last question on the test on Wednesday is an essay question, and it simply says, explain nuclear stability. What is nuclear stability? What's going on? So I'm basically going to talk you through the answer. If things get a little bit confused or need me to back up or redo something, just give me a shout. Okay? So the first thing we want to understand is what is meant by nuclear. Nuclear stability. What is meant by nuclear? Don't think too hard. Anybody have an idea? What's that? What part of it? The nucleus. Okay. So when we talk about nuclear stability, we're talking about the nucleus. Okay? And stability just means that energy is not being released, not harmful. Not sure other way to put it, so we'll leave it at that. Okay, so nuclear stability. So we're looking at what the nucleus, in the nucleus, and stable meaning nothing's harmful, there's no radiation, everything is kosher, nothing's happening, nothing physically is happening. All right, so what's in the nucleus? Let's start there. What's in the nucleus? Protons and neutrons. All right, very good. So let's do this. We'll draw a big nucleus, and we'll put protons in here. And let's start with just the protons. Okay, we'll do 5 of them. Just start with the protons. Okay, now what do we know about the protons? The positively charged. Okay, so we'll put some positive charges in here. Okay, so on your essay, you want to establish that protons are positively charged. You have to be able to, bless you, establish that. Okay, now here's the key. Positively charged particles in a small area. What do we know about positively charged particles coming together? What's going to happen? They're going to repel each other. Very good. So we have protons are producing a repelling force. This is in time for Star Wars, right? The Force. The Force be with you. Okay. The protons are producing a repelling force. So they are pushing away from each other with a force, a repelling force. So you kind of think of a balloon, right? If I blow into a balloon, the balloon kind of expands a little bit because there's a force inside, right? There's a pressure inside, right? So the more I blow the balloon up, what happens to my pressure inside? It gets more and more intense, right? So here, the same thing. The more protons I have, the more repelling force we're going to have. I'm going to use anthropomorphic connection here and call this tension. Okay, you're still going to recognize that there's a repelling force causing what we're going to call tension. Okay, tension. Okay, so the question is then, what is going to help these protons from pushing out so much in the atom, or in the nucleus, where it explodes the nucleus like a balloon? What else is in the nucleus? Neutrons. Okay, so we'll use blue for neutrons. So we have neutrons. We have neutrons in the nucleus as well. So you need to establish that there's protons in the nucleus causing a repelling force because they're positively charged, causing a tension. And now you talk about the neutrons. Anything special about the neutrons? What do we know about the neutrons? the neutral charge, right? They don't have any charge to themselves. So that's like, well, that doesn't seem like it's very useful. How many of you know what type A people are like? What's a type A person? Yes. A type A person reminds me of this repelling force in the nucleus. Okay? A type A person is very domineering. They're great leaders, kind of OCD. Everything's got to be a certain way. Their way is the highway. Even when they're wrong, their way is the highway. Okay? And I have a few friends that are that way. Even if you explain to them or show them that, okay, you're a little bit off on this one, they still think that they're right. You know anybody like that? Okay, some of us have maybe a slight type A personality, maybe not 100%, but at certain instances we might have that personality. Okay, so that's why I think with all these protons, if all these protons are type A people, right? They're kind of at each other. So think of what's the movie? Apollo 13. Bless you. Have you ever seen Apollo 13? A few of you. Okay, all right. So set the stage here. Apollo 13. The astronauts are coming back from the moon. They had some problems getting to the moon. They couldn't get into orbit. They had some malfunctions going on because something happened when they took off. So on the way back, they had other problems. One of the problems they have is that their CO2 filter broke. So carbon monoxide is kind of poisonous where you can suffocate and die. Okay, so they need to somehow fix this CO2 filter in their space shuttle coming back. So the scene shows as you have this small room and this big table, about 7 physicists, 7 very smart people, okay, who are type A people, right? They're very, very high strung, but they're experts in their field. So the scene shows as these 7 type A scientists are in this room. A guy comes in with a box, throws a bunch of stuff onto the table, and says, "Okay, your job is to create a CO2 filter with this stuff, because it's the same stuff that they have in the space shuttle, with this stuff, so that they can make it up there and survive. No pressure." Okay, so that's the scene. So you can imagine there's one task and 7 type A people trying to do one task. Can you imagine the tension in that room? Yeah, so you don't know what I'm saying? Okay, so everybody wants to do it their way, okay? Maybe at Christmas time you want to open presents a certain way. Everybody wants to do it their way, so there's always an argument. I want to do it this way, and I want to do it this way, and I want to do it this way, okay? So it's that tension going on, all right? So with all that tension, there's got to be something that we can do to kind of mediate that tension. Okay, you get the picture? That's kind of what I see inside of the nucleus. These protons are your type A people, right? And they're at each other, right? I want to do it my way. You know, you're wrong. I want to do it my way. So they're totally constantly at each other. So the neutrons then are going to be like a mediator. So we're going to send in a few mediators into this room of scientists and say, Asher, it's okay, calm down, calm down. Devin's a good person. You can work with him, okay? Calm down. Quit beating holes in the wall, all right? Elise Gray, stop yelling. It's okay. Work together. Okay? So these mediators come in and they kind of calm down our type A people. Get the picture? Okay, so that's kind of what's happening inside the nucleus here, is these neutrons are kind of like mediators, right? They're kind of calming down the tension of this repelling force of the protons. And from a science perspective, what happens is that they create, very important, they create a strong nuclear force. Okay, we're not sure how or why because they're neutrally charged, although more research now is looking into neutrons, what neutrons are made up of. Neutrons are made up of protons and electrons, and if you go even further, looking at gesons and mesons and muons, and it goes way beyond what we're looking at. But for us, we have to understand that these neutrons are creating a strong nuclear force. And this strong nuclear force is combating or stabilizing the repelling force of the protons. Okay, so you have to use those terms: repelling force, strong nuclear force. The neutrons are the mediators. They're going to come in and calm down my type A people here. Okay, and so that's my anthropomorphic connection. But in the science connection, the neutrons are creating this force. This force, the strong nuclear force, is stabilizing, if you will, or neutralizing the repelling force. Okay? All right, so we got the picture there? Okay, so now let's do this. Let's bring in 5 more protons, 5 more scientists into this room. Time is of essence, right? People are going to die up in the space shuttle. So now we're going to add 5 more protons here. Now what's happening to attention in my room? Getting pretty intense, right? Have you ever been into a situation where you feel, or maybe you're watching a movie, or maybe you're actually in part of a situation, sometimes at the end of the school year, you're in the cafeteria, you're an innocent bystander, but sometimes you feel tension going on, like there's something's going to happen, like one more thing happens and tension's going to break. Maybe at home, if you have siblings, right? Or exam week. How many get stressed out on exam week? All right, there we go. All right, so exam week, let's look at exam week. One more thing that happens, like it's typical Monday, you got exams coming up, and you're just stressed, right? You get home, your cat runs in front of you like it usually does, and you get upset, and you kick the cat because you're just upset, right? Something's going to set you off. Have you ever been there before? All right, you punch holes in the walls. Some of you get in your car and you drive, you listen to music real loud or whatever. Some of you will go run for 3 hours because it helps you out. Okay, you don't do that. I do that. Okay, something's going to give. Are you with me? Okay, so that's what's happening here. Inside of the nucleus, if we have so much tension going on that my mediators can't help out, they're trying to do the best they can with all my type A people. There's too many of them. They can't get everything stabilized, right? So what's going to happen? Well, there's a breaking point. At some point in the nucleus, at some point, there's so much tension going on that my strong nuclear force can't stabilize this. At some point, what's going to happen? Just like you do, what's going to happen on exam week? At some point, you're going to explode, right? You're gonna yell, punch a wall, go run hard. Something is going to happen, and that something's going to happen is radiation for us for this. Okay, something has to give, and what gives is that there is a release of energy. If I go run 2 hours because I'm so stressed out, I'm releasing energy. Okay, I think of Rocky. He's punching the punching bag, and you get done, you're exhausted. But he's released energy, and he kind of feels a little bit more stable. Okay, your exam week, you're so stressed. Maybe you eat a lot. Maybe you go take a nap. Maybe, like say, you listen to music. You do something to decompress. All right. What do you guys do to decompress? I know you don't run a lot. Take a nap. That works because you're so exhausted. You take a nap, right? What else do you do? What do you do to decompress when you're so stressed out? Eat ice cream. Read a book. There you go. Like it. You get your mind off of things, right? What do you do? Or you got a question? Go ahead.
Yeah. So when the protons pile up, that's when it.
Okay, so it's not so much when the protons pile up. This is what's happening. When the strong nuclear force can no longer stabilize the repelling force, whatever condition that is. We might have more protons than neutrons. We might have more neutrons than protons. At some situation, okay, here's the key. Some situation, the strong nuclear force cannot stabilize this repelling force from the protons. At that point, we have release of energy, right? Stressing, kind of decompressing. That releasing of energy we call radiation. Alpha and beta that we're going to get to. Okay, so that's kind of your essay in a nutshell. Can you go through it again real quick? You got it? Got it? Yes, sir.
This explains alpha radiated. I assume at some point we'll get to how this relates to gamma radiated.
Not gamma. We're not going to go that far. Just, yeah, we're going to keep it basic, alpha and beta. Alpha and beta. And you'll see that in geology. You might have already seen it in earth science. I don't know how deep to go with earth science with that. Okay. Okay, got the idea? All right, now I need you to get your periodic tables out because now I want to show you something that connects to this. While you're doing that, again, back to the essay, I'm looking for what's happening, what's in the nucleus, protons and neutrons. You're going to explain to me protons have a positive charge. They create a repelling force or quote tension. The more protons we have, the more tension we have, the more problem we have inside. The neutrons are there. They're neutral charge, but they create a strong nuclear force. These forces are opposite of each other. The strong nuclear force is, quote, stabilizing this tension. At some point in time, this is important, at some point in time, the strong nuclear force cannot stabilize the repelling force. Doesn't matter how many of neutrons we have in there, okay, they can't stabilize that repelling force. Okay, so that's kind of what you need to talk about. Now, how does this work on the periodic table? Let's look at the periodic table. And I want you to come up with a ratio of protons to neutrons. Protons to neutrons. Okay, protons to neutrons. We're going to do a comparison here. So let's look at lithium. How many protons does lithium have? 3. How many neutrons does lithium have? 3 to 4. Okay. Let's look at nitrogen. How many protons does nitrogen have? How many protons? Okay. Let's look at fluorine. How many protons? How many neutrons? 9 and 10. Okay. Let's look at magnesium. How many protons? How many neutrons? 12. Okay, let's look at chlorine. How many protons? Neutrons? Chlorine. Mental math, what is it? Come on. 18. All right, 35 is our mass number. Okay. All right, so 1 through 20 on the periodic table, our ratio is roughly 1 to 1. Okay, our ratio is roughly 1 to 1. So for every 1 proton, we have 1 neutron that can help stabilize each other. Okay, now let's go beyond 20. So let's go beyond 20. Let's look at bromine. Let's look at bromine. Bromine has 35 protons. And how many neutrons does it have? 45 neutrons, okay? 1 to 1 ratio? Yes or no? No, not 1 to 1 ratio. So we have a lot more neutrons in nature now that are stabilizing the 35 protons. So the more protons we have, the more repelling force, the more tension we have inside the nucleus, okay? So the tension is getting bigger, building inside the nucleus. So I need more neutrons to help stabilize that. Got it? All right, let's look at zirconium. Zirconium. It's got 40 protons. How many neutrons? Momentum math, what is it? 51. Okay. Let's look at iodine. 53 protons. How many neutrons does iodine have? Is that 70 something? 74? Okay. How about mercury? Okay, 80 protons. It's got a lot of protons. humid's bugging me here. How many neutrons? 121. Okay. What's happening to my ratio here? It's getting a lot bigger, okay? It's getting huge. So the lot more protons we have, we need a lot more neutrons to help neutralize those protons, okay? Again, at some point, what's going to happen, though? At some point in the nucleus, what's going to happen? Think of your exam week. You're going to have at some point, there is not enough neutrons that are going to stabilize the protons, okay? There is a stress breaker, if you will, okay? A stress breaker. And that happens to be 83. So from bismuth and on, so 83 and above is considered radioactive. Okay, so we'll put equal to or greater than number 83, which is bismuth. Okay, so theoretically, at 83 protons on the periodic table, from 83 on are considered radioactive. Again, some are very harmful, some are not so harmful. We haven't even talked about the isotopes yet. Some isotopes are stable, some isotopes are not stable. Okay, again, it goes into that ratio between protons and neutrons. If the neutrons cannot create enough strong nuclear force, then we have radiation or radioactive elements. All right, let's back up a little bit. Any of that doesn't make sense to you? And you have to explain it. It's a good essay. You have the question ahead of time, went through it in detail. I want you to get 100% on the essay Wednesday. I would put this, maybe not so much. You could say, at the end of the essay, you could say that on the periodic table, the ratio between protons and neutrons are enough to stabilize the atom until you get to number 83. At that point, there's not enough strong nuclear force to stabilize the repelling force. Okay, but what I'm really looking for is that you tell me that at some point there is a breaking point. There is a point where there's not enough stability in the nucleus, and then we have that radiation, spontaneous releasing of energy, right? These atoms are spontaneously releasing energy, okay, because of this, because the ratio isn't intact. Now, just like me, when I go run 2 or 3 hours on my stress days, I get back, I've released energy, and now I'm more stable. Okay? When these atoms are releasing energy, their goal is to become more stable. So as they're releasing energy, they finally end up as a stable state. Okay? Okay, so that's the essay part. The last part we have is nuclear equations. And half-lives. Okay, nuclear equations and half-lives. It's the last thing we have to do. So I have a worksheet. The one side I want us to focus on, it gives a great picture, the visual of what's happening. Okay, so look on the side where you get this picture of the atom. It says 226 Ra88. An arrow. So we have this picture, this diagram of this radioactive element. Okay, so it has all these little shards coming off of the nucleus. So we have protons and neutrons inside. Okay, and it's radioactive, which means it's releasing energy. Now on the other side of the arrow, it shows the same structure, but it says plus, and then it has an alpha particle coming off. Okay, so this structure is something else over here plus an alpha particle. All right, so I'm just taking the picture that you see here, and I'm going to write it into what we call a nuclear equation. So this structure is losing an alpha particle. See the big chunk out of it? Okay, see a big chunk out of it there. So this substance is radioactive, and it is losing an alpha particle. So this is what we call an alpha decay. An alpha decay. Because an alpha particle is breaking off of this substance, right? It's releasing radiation. It's unstable. It's releasing radiation in the form of an alpha decay or alpha particle. An alpha particle, we talked about, is a helium atom. Okay, a 4 and a 2 for our numbers. Everybody see that? Now, when we write a nuclear equation, it's like in math class. The arrow is like your equal sign. So something on this side has to equal something on this side. Okay, so here we go. What do we call this number up here? What do we call that number? That's the mass number, okay? The mass number on the left side of the arrow, whether I have one substance or multiple substances. The sum of the mass numbers on the left side of the arrow has to equal the sum of the mass numbers on the other side of the arrow. Same for the atomic number. The sum of the atomic numbers on the left side, so if I had multiple substances here, I have multiple mass numbers, equals the sum of the mass number, or atomic numbers on this side. You all wrote that down? The sum of the mass numbers on the left side, whether I have one or multiple substances, the sum, what do I mean by sum? Add them together, right? You're adding summation, add them together, has to equal the sum of the mass numbers on the product side. And then for the atomic numbers, same thing. The sum of the atomic numbers on the bottom, on the left side, has to equal the sum of the atomic numbers on the product side. It doesn't matter if I have 5 substances on the left side and 2 substances on the right side. That's the goal. And again, when I go through this, it'll make more sense. Okay, so this is what you're typically going to see. You're going to see a setup like this, and I want to know what that substance is. What is my remaining substance? If I go through an alpha decay, I know the alpha decay, I'm breaking off a helium atom. Okay, what do I have left? Okay, so how do you do that? Remember, the sum of the mass number on the left side has to equal the sum of the mass number on the product side. So if I have a 4 mass number here, and this is 226, what is my new mass number going to be? 222. Because 222 plus 4 gives me 226. The summation of my mass numbers has to equal the same on both sides of the arrow. The next thing I'm going to do is my atomic number. If I have 88 here, I have 2 here. What's my new atomic number? 86. Very good. So the first thing that you're going to do is figure out the new mass number and the new atomic number. The second thing you're going to do is now identify that new substance. Okay, it's also on your page there. What is number 86? Look on the periodic table and you get Rn, right? Okay. So an alpha decay means that this substance is going to release energy in the form of alpha particle, and this is what we call a nuclear equation. Your job is to figure out what that missing substance is, okay? We're not going to go through a whole cycle of radiation until it's stable. We're just going to do a one-step process, okay? Let's have you do this one. We're going to go uranium-238. And uranium-238 is going to go through an alpha decay. An alpha decay. I'd like for you to show me the nuclear equation for an alpha decay for uranium-238. All right, give that a go, and we'll check it together. Right, an alpha decay for uranium-238. Go ahead and check with your neighbor. If you didn't get it, have them talk to you, okay? Because I just explained this, and some of you have a blank paper. You need to take your notes and apply it. Okay, so here's what you do. I'm going to give you a substance like this. I'm going to tell you it's an alpha decay. So that tells me that an alpha particle is breaking off of this. Okay, you can write it this way, or you can start with the helium atom first. Some people like to start with this first because that tells them right away it's alpha particle. It doesn't matter which order. Okay, and then it's going to be added to my new substance. So if this is 238, I have 4 here. This becomes 234. All right, 234 and 4 gives me 238. And this becomes 90. 90 plus 2 gives me 92. And I think it's thorium for that. Okay, get the picture of how to do alpha radiation nuclear equations. Okay, notice that I did not put uranium plus helium equals whatever. On tests, I get that all the time. I don't know where it came from. Because if you don't see it here, it's not going to be an answer on the test. Okay, so don't change what we did. All right, some of you will do this. Okay, that is not what we did here. Okay, but some of you would do that. Don't do that. Okay, and some of you would do this. Arrow, arrow. We did not show that here. Not going to be an answer for you. Okay, so don't change what we do up here for something different. Okay. All right, now we're going to do the same thing for a beta decay. Beta decay. So let's do carbon-14. All right, I want to do a beta decay for carbon-14. Okay, a beta decay for carbon-14. So we're going to do the same method as we did before, but instead of using a alpha particle, we're going to use a beta particle. Okay, what is the symbol for a beta particle? Two people. What do you got, Asher?
091.
Perfect, okay. So 0, -1, I'll use the E symbol. 0, -1, okay. Now, what is my new mass number, new atomic number, and new substance? Get an answer, check with the neighbor, please. What's the new mass number, new atomic number, new substance? Same process we did with the alpha particle. Mass numbers has to equal the same on both sides of the arrow. Atomic number should equal the same on both sides of the arrow. All right, top number is going to be what? 14. So 14 plus 0 is 14. That's good. I'll tell you why this is 0 in just a second. What's my bottom number? It's got to be 7. 7 minus 1 gives you 6. Okay, so this is a -1. So be careful of that. And this is going to be nitrogen, right? Okay, that's a beta decay. Now, during a beta decay, I want you to understand this. During a beta decay, we have a neutron that's going to break up. During a beta decay, we have a neutron that's going to break up. It's going to split. It's going to split into a proton and an electron. That neutron from carbon is going to split into a proton and an electron. What's the definition of a beta radiation? High speed electrons, and there you go. The electron is not being dispersed from the structure of carbon. It's being dispersed from the neutron in the nucleus. Okay, so let me show you this. Carbon, okay, it has 6 protons and 8 neutrons, right? Carbon-14. Okay, now over here, we said that this neutron is going to break up, right? So now I no longer have 8 neutrons. How many neutrons do I have? I have 7 neutrons now because this neutron broke up. Okay, and how many protons do I have now? 7. And that gives me my new substance. Isn't that cool? Because a neutron inside the nucleus breaks up into a proton and the electron. The electron is released, and that's why I feel that's my radiation, okay? And then the proton is in my new structure, and that's how I get my neutron. Okay, let's do this one. Let's do a beta decay for radon-227. Let's try that one. Again, check with the neighbor once you got it. Also, I like that some of you are actually writing little notes to yourself through the process of this. That's awesome. and some of you have just what I have on the board. Again, that's not going to help you. If you have just what I have on the board, that's not going to help you in a couple of days from now as you review. Okay? You want to write a little notes to yourself of why we did what we did. That's good note-taking skills. So you go back tonight, after a full day of information from all your classes, some of this is going to get a little bit muddled. Okay? You need to have something to kind of trigger what we talked about today. All right, so we have a beta decay. So we're going to go 0, -1, E. My mass number is not going to change. My bottom number is going to be 89. And that symbol is going to be AC actinium. Okay. Got it? All right, so here's the deal. On the worksheet I gave you at the beginning, on the back side, you have practices that write an alpha and beta decay, 1 through 10. Okay, that's due tomorrow. Okay, so you have the rest of the class hour to get that done. Tomorrow when you come in, we're going to take the quest, element quest. We're going to grade this. Then I'm going to go over half-lives with you tomorrow. And then you're going to have a worksheet for about 20 minutes that's going to review the half-lives and the nuclear equations. And then any time after that, if you have questions for the test, you can ask. Okay? Now I'm going to give you a study guide, okay, for the test. The study guide is pretty close to the test, except for a couple of things. Okay, and I'll tell you what those couple of things are as soon as I pass these out. No, sorry. On the worksheet, you're only going to do the back side where it says write the nuclear equations 1 through 10. The front side with the picture, that's just a picture for you to visualize. You do not need to do questions on that page. Okay, just the back side 1 through 10. Put your extra in there for Travis. Okay. Okay, so on the study guide, study that. If you can do the study guide really well without your notes, you're in good shape. On the test, I added a couple questions from the review questions 4.1 and 4.2. I did a little bit out of sequence from last try. I did this section a little bit later, but I decided to do it first time for the first unit here. So 4.1 and 4.2, you had those. You had to read and take notes, and then we did all of those reading questions. Then I gave you the group together review quiz. Okay, so a few questions from that, and then half-lives that we're going to do tomorrow. Okay, now the half-lives is that you can do it conceptually or you can do it mathematically. So if you recall this from algebra class, you're in good shape. If not, we'll go through the conceptual part tomorrow. Okay, so there's a couple questions on this on the test, and then 1 or 2 questions on the half-lives on the test. Okay, so those two. Those you already have. This one we're going to wrap up tomorrow with. All right? All right, so there you go. So you got tonight and tomorrow to get ready for the test. Like I said before, though, you should have been preparing for the last 4, 5, 6 days because you knew it was coming up. So hopefully you're not so stressed